and it's quite a powerful tool. I said that it's not only MRI. This is an example of some early work with electrical recording in neurons, and you can, by recording, in this case, monkeys, you can demonstrate blips in their learning processes. So reward is quite important in learning, and synapses are critical. I mentioned the pathways. You know, we have a vast number of 100 billion neurons stored in the brain, and each of these are connected to other neurons. Each, on the whole, will be connected to around 2,000 other nerve cells. So what you're looking at in the brain is a telephone directory immensely more complex in its connections than the entire city of New York, far more complex. Those new connections are being made all the time, and the reason why your brain sort of changed when you walk out of here is because you will have made new connections that you didn't have before in your brain this afternoon and this morning. And here's a little film clip about it. Sorry.
Learning something new means rearranging the way her brain works. Our brain has an astonishing 100 billion neurons, or brain cells, all connected together. Learning is about creating and strengthening pathways through these neurons for impulses of electricity. But between each and every connection in our brains, there's a tiny gap called a synapse. For any of us to learn something new, the electrical signal has to jump across this gap to continue its journey.
The gap between the two brain cells is tiny, but that doesn't mean that it's straightforward for a signal to get from one side to the other. For us, it's like crossing a deep ravine.
I'm going to try to get from one side to the other, and how I do it should tell me something about the way we learn. The first time a signal crosses from one brain cell to the other demands the most effort, and it's the same when we cross our ravine.
The first trip across is the hardest. Having crossed the ravine once, the journeys across get easier and easier. And a similar thing happens when we learn something.
To start with, learning is difficult. As the signal crosses the gap between the brain cells again and again, we establish a more solid pathway.
Sorry about that. By the time we've made the crossing over and over again, it becomes effortless. We can do it whenever we like. We finally learned something. That clip tells you two things. First of all, it tells you that repetition, that's how repetition works, because it reinforces those connections in the brain. And of course, the other thing the clip tells us is that very often a visual metaphor, which is what I'm using there, is useful in learning. So the possibility is that some of you will remember that visual metaphor, even if you forget the word synapse. And that is part of the learning process. So forgive me for showing a rather self-indulgent long piece to camera of my own, but I think the point is made well with it. And that's something that's worth bearing in mind.
It's one thing to fill your brain with facts. It's quite another thing, though, to remember them. So how do we do it? Well, memorizing something is rather like what happens when we set up a line of dominoes. When we commit a fact to memory, we create a neural pathway to it, a route of connecting brain cells to wherever that memory is stored in our brain. And to retrieve those facts, all we have to do is to trigger the same pathway back to them.
The page is setting it up.
It sounds easy, and for some people at least, it really is. This is Andy Bell. In 2002, he was crowned World Memory Champion. But just how good is he? Today, we've set him a test. He's going to try to recall the exact position of every single card in 10 whole decks. That's 520 cards that have been shuffled by us. And he's only got 20 minutes to look at them. Andy has developed a special technique which allows him to remember literally thousands of items in rapid succession. The 20 minutes are up. Can Andy remember the position of the cards our referee selects at random?
So, deck one, the very first card you saw.
First card was the 6 of spades.
Same deck, card number 23.
The 23rd card was the Queen of Hearts.
Deck two, card number 27.
Ten of Diamonds.
No matter how many cards we fired at him,
That was the King of Diamonds.
Andy remembered them perfectly.
48th card was the Ace of Hearts.
In fact, Andy is able to recall
10 clubs.
all 520 cards.
Jack of Clubs.
Every one correct and in the right order.
Queen of Spades.
So, what's his secret?
What's his secret? Well, that's very interesting. The secret of the memory and learning there is to identify with each card a place in one's mind, because our positional sense is evolved through evolution. Early on in the savannah, we would be learning very vigorously where we are geographically. And so what he says is that the King of Spades is, let's say, Waterloo Station. And let's say the Jack of Diamonds is Princes Street in Edinburgh. The Three of Clubs is his home street, let's say Stuart Street in wherever he lives in Bedford. And so he's taking a journey. You know, you remember I mentioned the journey at the very beginning, and that journeying is part of the process of learning, because our spatial memory is very, very deeply embedded, and that's one alternative pathway in the brain. There are many different ways of getting that alternative pathway, but Andy's particular way of doing it works very well for some people, not for everybody. Different people have alternative pathways. So it's not merely just learning by rote, it's actually learning by using as many different pathways to arrive at the same destination as possible. Another issue, unquestionably, is empathy in learning. This is a lovely experiment done by Tanya Singer, also at University College London. And what she's done is she put lovers or partners or husbands and wives in a scan at the same time and deliver somewhat painful electric shocks to one of them. Not a very pleasant experiment. But what happens, of course, is that the partner watching has the same activation and the same blood flow through the pain centers. So they are actually experiencing the pain. And it's true, of course, with pleasure and with learning as well, that if you empathize with the person who's teaching you, if you actually have a relationship which is favorable and you feel encouraged by them, that relationship is very, very important in the learning process. And one of the issues, of course, also, and I just want to deal on this briefly before I close, is the current problem. This is an American paper, but it's shocking to think that hunger is still a national problem with children in the United States, actually as it is in Britain too. And it turns out that that deprivation of essentials can change our learning in all sorts of ways, not just simply in the food for the brain, but actually in the environment in which we live. So in fact, having the right environment is particularly important. And it's shown brilliantly in this experiment by Champagne. Champagne is François Champagne is in McGill University in Canada. Now, what she's done is, I think, one of the most fascinating experiments in the field. She's taken mice, and she's done this with rats as well, and it probably would work with humans. And she noted that some rodents are very low grooming, that is, that they don't lick and groom their young in the way that most mothers do. And so the low grooming mice she removed from their litter and replaced them with high grooming mice, switched them round so that the newborn mice were with a low grooming or a high grooming mother. And of course, obviously you have to find the low grooming mothers because most naturally groom in a high grooming fashion, some don't. And then she looked at the brain, and she looked in particular at the estrogen receptor in the preoptic nucleus. It doesn't matter where it is, but it's in the front of the brain here. And it turns out that what she was able to demonstrate was that there's no change at all in the DNA. The lettering in both the high-groomed animals and the low-groomed animals is the same. But there are areas where the DNA is not working properly. So it's not a question of the genome, it's a question of how the genes are actually working. Now, what's fascinating about this is that the low-groomed mice learned, when they were adults, less well. And that's a very important piece of epigenetic information. And what's more important, and worth bearing in mind, that these mice, when they gave rise to their own children, so the grandchildren of these poor grooming mothers, also learned less well. It was heritable. The DNA did not change, but the way the brain functioned was in fact permanently impaired. Now, I think that's a very likely phenomenon, not just in mice. Mice and humans are very close. The mouse is a very standard model for these sorts of experiments. And many of these experiments are not at all inhumane. There's nothing remotely about animals suffering. And we can learn a lot from that kind of observational science. But it should tell us a great deal about some of the issues about maternity. Now, what about the future, just finally? Well, one of the things we're doing in my laboratory is changing the genes in mice by genetic modification. This father mouse has a dominant gene for a black coat. So, according to Mendelian theory, all his children should have a black coat, but they don't. They have a brown coat. All four of them have a brown coat because we've changed a particular gene which they carry in their sperm, and so they now don't any longer pass that dominant gene on. And we've now had a very efficient way of doing this. And it's interesting to consider what that might mean in terms of intelligence and learning. We now know of at least 25 different genes which are associated with learning. And the thought of actually enhancing or changing the way those genes express in animals, and of course eventually possibly in humans, is really quite alarming as well as a promise. It's a promise and a threat. Just to give you an example of the power of this technology, I want you to look very briefly at this next film clip.